Hello physicists and welcome. In this session we're looking at accelerated motion. We'll look at completing the position versus time graph from information from a velocity versus time graph. Information we're given is velocity versus time. We'll be looking to use the area of the velocity graph to find displacement, and additionally we'll use the velocity versus time graph to calculate the acceleration. Let's get started. The information we're given here is the velocity versus time. At a time of 0, we can see we're moving at 2 meters per second. At 1 second, it looks like we're moving 4 meters per second. At 2 seconds, we're moving at 6 meters per second. Let's go ahead and complete our table here. So we're moving at 4 meters per second, 6 meters per second. Let's go ahead and complete this. Hey, so let me transfer the information here. My initial velocity is we're not at rest. We're actually moving at 2 meters per second at a time of 0 seconds. So our initial velocity is 2 meters per second. Our final velocity, we can see after 6 seconds, is 14 meters per second. And the change of time from 0 to 6 seconds is 6 seconds. Hey, we'll look at the acceleration. Our acceleration is our rate of change of velocity, or we could say our change of velocity divided by our change of time. We could also say that as our final velocity minus my initial velocity divided by my change in time. Let's go ahead and put the numbers in we have here. My final velocity, 14 meters per second. There we go, minus 2 meters per second, and we'll divide that by our change in time, 6 seconds. 14 minus 2 is 12. Getting a little bit crowded here. I'll write it down here. 12 meters per second is my change of velocity divided by my change of time. 6 seconds, 12 divided by 6 is 2, and then my units, meters per second per second. Be careful with a positive sign. What does it tell us? That our boat is increasing its speed 2 meters per second every second. So we get these units of meter per second per second. You may also see this listed as being 2 meters per second squared. We're going to use the area of the velocity graph to find displacement. We'll look at the total displacement of the boat. Hey, and we have some information here. We have an initial position of the boat is 4 meters. Remember, velocity doesn't tell us anything about position. It tells us about our change of position, but it doesn't tell us about our position. So we do have some information here. 4 meters is our initial position. We want to know what the final position of the boat is. We can end up filling that out over in the table here. So our initial position is 4 meters. We'll go ahead and record that. Now we're trying to figure out our total displacement over those 6 seconds. Hey, back in our constant velocity days, it was pretty easy to figure out displacement. Our displacement was just an RTD problem, was our rate of velocity, and I'm just going to call it my average velocity because I have some ideas in mind here, times my time. Now our velocity didn't change in constant velocity, but here it ends up changing, so we have to use another technique. And we saw in the previous videos that the area of the velocity versus time graph gives us displacement. Now in an earlier video, we typically had these as forming triangles because we started at a 0 velocity and then we increased. But we can figure out the area of these trapezoids as well. Hey, I took a moment to clean this up. But if I want to figure out the area, and remember our area here has the units of the height times the base, so a meter per second times seconds. Hey, that's going to give us a value of meters, which is what we measure our displacement in. Now this trapezoid has a little more difficult formula than the area of a triangle, but we know that the area of a trapezoid is equal to height 1 plus height 2 divided by 2. That actually gives us our average height times the base. In this case, our height 1 is the height over here. Height 2 is the height over here. And our base is the time. Let's go ahead and figure this out. Hey, height 1, we can see from the table, is 2 meters per second. Height 2 is 14 meters per second. And the base is 6 seconds. Let's go ahead and put those numbers into our area formula. Hey, so I have 2. I'm going to leave off the units just for space consideration right now. 2 plus 14 divided by 2 times 6. Let's go ahead and we'll put that in our calculator to figure out what that is. So 2 plus 14 is 16 divided by 2. So we have 8 times 6 is going to be equal to 48 meters is equal to our change of position. So our position at 6 seconds is going to be equal to our initial position, 4 meters, plus our change of position, 48 meters. So we're at 52 meters. And you can see these other positions have this star here. Don't worry about filling those out or calculating it yourself. But if you do want to see how it's done, we can use that same technique. Okay, so go from 0 to 1 second. Okay, I went from 2 to 4 meters per second. 2 plus 4 is 6 divided by 2. That would be 3. 3 times the base of our trapezoid. 1 tells us our displacement is 3 meters. 3 meters plus our 4 is 7 meters. 12 meters at 2 seconds. Let's do it again a little more detailed at 3 seconds. I started at 2 and went to 8 meters per second. 2 plus 8 is 10 divided by 2 is 5. 5 times 3 seconds tells me I went 15 meters plus my initial 4 meters. I'm at 19 meters. And I'll fill out the rest of the table here. Okay, so let's come back over here. So the total displacement of the boat is our 48 meters. We calculated here, our 48 meters here. So the displacement from its initial position, 48 meters. And the final position is that 48 meters plus our 4 meters in our starting position. We're at a position of 52 meters. And now we have the note. Now draw the position graph. Let's go ahead and do that. It looks like we're going to have to go from 0 to 6 seconds here. And if we go 10, 20, 30, 40, 50, 60 meters along here, that'll work out pretty well. I'm going to label the graph. Let's go ahead and produce our graph. At 0 seconds, we're at about 4 meters. At 1 second, we're at about 7. At 2 seconds, at 12. 3 seconds, 19 meters. 4 seconds, we're at 28. 5 seconds, 39. And 6 seconds, we're at 52. Hey, if I make a best fit line through here, I'll try doing that. Okay, I've gone ahead and drawn that best fit curve. This is a parabola. It has an initial slope because we're starting at 2 meters per second. It gets steeper and steeper because our velocity is picking up. Let's go ahead and draw our motion map. Hey, we're going to have to cover from 0 to 60 meters. So if we start off at, so it goes 0, 10, 20, 30, 40, 50, and 60 meters in that direction. We'll go ahead and label it with our positions. Hey, so at a time of 0, I'm about 4. At a time of 1, I'm at 7. At a time of 2, where are we? We're at 12. At a time of 3, 19. At a time of, what happened to that one? Okay. At a time of 4, 28. At a type of 5, we're at 39. And at a time of 6, we're out at 52. You can see our dots are getting further apart. Try putting in my arrows now. Okay, each arrow is getting longer, indicating that we are speeding up. And if I can, I'll label that with our time of 0, 1, 2, 3, 4, 5, and 6 seconds. So there you have it. Everything you need for filling out, what is this, page 12 in the packet. And just a couple of last-minute notes here. Almost forgot about them. Hey, so we see that the boat is moving in a positive direction. The velocity is always positive, so it's moving in a positive. I'll just put the plus sign, positive direction. And we can see that the velocity is always increasing, so it is moving in a positive direction. And speeding up. And so earlier I had mentioned, hey, don't worry about the actual calculation for all of these intermediate points. Okay? But it is important to know that these do not form a straight line, but end up forming that special curve. So what you'll be required to show is how you can calculate the value at the end. And we could do that one. We'd know that what the value is here. We know what our starting point is. And if you don't calculate all the points in the middle, just know that it ends up having a curving line. If it's speeding up, it curves up. If it's slowing down, it'll curve downward. All right, so just want to make sure I got those points in. And for now, that's physics.